Across the planet, the physical power grid strains. New transmission lines snake through untouched landscapes. Substations expand. Utilities face unprecedented demand, driven by an insatiable hunger for computation. But the most extreme engineering challenge isn't routing thousands of megawatts across continents. It's routing 1,000 amperes across a space smaller than your fingernail. Most people think the future of artificial intelligence hinges on software breakthroughs, on clever new algorithms, or simply on printing more transistors. We imagine a world of pure data, of abstract calculations. But that's where everyone is wrong. The true bottleneck for AI's next frontier isn't conceptual math. It's the brutal, unforgiving laws of physics. Specifically, the physics of electricity, confined to the smallest possible spaces. Today's cutting-edge AI chips, like those powering the next generation of large language models, are demanding well over 1,000 watts of power. But here's the kicker. They operate at incredibly low voltages, typically around 0.8 volts. Do the basic math. Power equals current times voltage. This means these postage stamp-sized pieces of silicon must draw over 1,250 amperes of current. To put that in perspective, a typical home's entire electrical panel manages only 100 to 200 amperes. We're trying to force more than 10 times that current through a microchip, and this creates a cascade of previously unimaginable engineering challenges. When you try to push 1,250 amperes through an impossibly small space, several fundamental physical problems emerge simultaneously. First, there's voltage drop. Every conductor has resistance, and resistance causes voltage to drop along its length, starving the most distant parts of the chip. Then there's heat. Resistance also generates heat, threatening to melt the microscopic structures. But two more subtle, yet equally destructive, effects dominate at these scales: the skin effect and the proximity effect. Imagine a massive, multi-core power cable buried deep underground. Engineers meticulously model these cables down to the millimeter because current doesn't flow uniformly. At high frequencies, electrons actually migrate to the surface of the conductor. That's the skin effect. And when multiple conductors are close together, their magnetic fields interfere, pushing current to one side. The proximity effect. These phenomena, once primarily concerns for utility companies and submarine cables, are now the defining challenge inside your microchip. The same physics, scaled down a millionfold. For decades, microchips used a relatively straightforward method for power delivery: lateral power delivery networks. Power, ground, and control signals all entered the chip from its perimeter, typically through tiny gold bond wires or solder bumps, then distributed across the chip's surface on dedicated metal layers. This worked beautifully when chips consumed tens or even a few hundred watts. There was enough physical space for wide, low-resistance power rails. But as power demand skyrocketed past a kilowatt, this lateral approach hit a hard physical wall. There simply isn't enough room on the top surface of the chip package to bring in 1,250 amperes without creating unacceptable voltage drops, catastrophic heat, and impedance spikes that destabilize the entire system. It was like trying to funnel Niagara Falls through a garden hose. To overcome this fundamental physical barrier, engineers have been forced to rethink the very architecture of microelectronics. The solution is radical. What if we stop trying to cram all that current onto the chip's top surface? What if we instead deliver power directly from the back of the chip? This is the concept of vertical power delivery, or backside power delivery. By bringing power straight up through the silicon, you drastically shorten the distance current has to travel, reducing resistance, inductance, and critically, the voltage drop. It's like switching from a winding mountain road to a direct elevator shaft. But building this elevator shaft inside silicon, at a microscopic scale, required another ingenious solution. The most promising breakthrough in this vertical power delivery challenge comes in the form of what researchers are calling package-embedded coupled inductor arrays. This is where the magic truly happens. Instead of relying on external power regulation components, tiny, multi-phase power converters are now being built directly into the chip package itself. Imagine miniature spiral square inductors, not much larger than a grain of sand, sharing a common magnetic core, all integrated within the substrate. These inductance islands are meticulously designed to handle the enormous, fluctuating current demands. When an AI chip suddenly needs a burst of power for a complex computation, it creates a massive, rapid transient demand for current. These coupled inductors respond instantly, preventing the catastrophic voltage dips that would otherwise lead to errors or system crashes. It's an intricate dance of electromagnetism, precisely choreographed to keep the voltage perfectly stable, even as the current surges by hundreds of amperes in nanoseconds. From massive utility grids battling to expand, to power cables modeled down to the millimeter, the physics of power delivery is relentless. The fact that engineers can now route over 1,000 amperes through a piece of silicon the size of a postage stamp, without melting it or collapsing its voltage, is a testament to the unseen frontier of modern computing. It's a battle fought not in lines of code, but in the intricate electromagnetic fields of microscopic conductors. These hidden breakthroughs in power delivery networks aren't just incremental improvements. They are the fundamental enablers for the next generation of AI, allowing us to push beyond theoretical limits and into a new era of computational possibility. The future of AI, it turns out, is less about abstract intelligence and more about very, very good plumbing for electricity.